Yes, class. Am I audible to all of you? Nuha, Leena, Mariam.
Yes, ma'am.
Screen is also sharing.
Yes,
Yes,
ma'am.
ma'am.
Yes.
For this, I wasn't able to share the screen. That's why I wanted to confirm. Okay. Last topic from gravitation, then we'll start with solids. Meanwhile, in your thermal batch, thermal properties of matter will be going. Here, second book will be started with the first and second lesson. That is chapter 9 and chapter 10. Fluid mechanics, solid mechanics. Solids we'll do first. It's a very short lesson, easy lesson. You all will be able to manage. Very easy. Okay. Yes, Kepler's law of planetary motion. See, when an object revolves, we can consider, suppose this is an object. This is revolving around it. Fine, this one is revolving around it. So if it revolves like this, complete proper circles, we call it circular orbit. Planetary orbit is elliptical. So when elliptical orbit is formed, then you don't have the center of the ellipse. Like we have the center of a circle. You cannot have one center of ellipse. What happens is that we consider two portions. Just a second. We consider two portions. First law says that planets revolve around the sun in elliptical orbit. Fine. Now, when we talk about ellipse, you have to understand few things. One diameter is this, one diameter is this. Like in a circle, if you take any diameter, across every diameter, you will be getting the same value. If you see across every diameter, if we are talking about circle, any diameter you consider, you will be getting the same value, right? Now here what happens, here you do not get it because it is ellipse. One side is narrower, other side is broader. So that minimum small diameter is called as the minor axis. The bigger diameter is called as the major axis. So you have two axes. Fine, you have to be careful with it. You have two axes. Now half of major axis, like the radius, which we use the term radius for it. So radius, or you can say semi-major axis, half of the major axis. Similarly, half of minor axis, semi-minor axis, which acts like a radius. This is semi-minor axis, this is semi-major axis. Now, two foci will also be there, like the center has a focus in a circle, but here two foci are present because one cannot be at the center. So what happens is that the sun is at one of the foci and the planet is revolving. Suppose sun is here. So here the planet is coming, then going. So this distance is greater, then it is coming, revolving like this. So at one of the foci, sun will be present for one of the orbit. All right, depending upon every planet has its own orbit. Use this basic you all. Now see, the edge, the periphery of the orbit, the edge circumference or the periphery of the orbit, which is located toward the larger radius, we call it as aphelion. All right. The second one, which is located towards the shorter distance, because see, if it is located at one of the foci, one will be nearer, one will be far away. We are just considering one of them right now. One will be nearer, one will be far away. One edge, the edge, periphery, this will be the orbit. Like this, you will have the orbit. This distance will be more, this distance will be less towards the periphery. Here the sun is. So this edge, no, which is very close to the sun, this is we call it as perihelion. And the longer one, we call it as aphelion. All right? Perihelion and aphelion. So planets revolve around the sun in elliptical orbit and the sun is present at one of the foci, any one of the foci depending upon it. This is Kepler's first law. Second law says that aerial velocity is constant. Aerial velocity means normal velocity means distance covered per unit time. We call it as velocity. Aerial velocity from the term area. Instead of just the distance, it is covering the area. So if a revolution is made like this, I am talking about the angle swept. Suppose this much of area has been swept. That change in area per unit time that rate of change in area, that we'll call it as areal velocity. So a second law says that areal velocity is conserved, areal velocity is constant. Change in area by change in time will remain constant. Delta A by delta T will be constant. All right, this is one law. So how is it helpful? A1 by A2 is A1 by T1 is equal to A2 by T2 is equal to A3 by T3 and so on. You can add it. Though here you will have only two, A1 by T1 is equal to A2 by T2. Questions also on this topic are like this only. You have to find out one of these quantities. And yes, one condition is that when this is conserved, external torque should be zero. Like in your system, no other force is acting. Net torque is zero. So if net torque is zero, angular momentum is conserved because angular momentum is the rate of change. If change is not there, force is only not present, your angular momentum will not change. So it's conserved. So these are the few factors that you have to remember about the second law. One numerical we'll do from the third law. From the second law, you will get numericals, but numericals will be very easy. Either one area will be given, one time will be missing like this. Just use this. So I'm not practicing any numerical on this because direct, exact, ditto formula based numericals are there. Let's let's skip to the third one so that here I want you to practice one numerical easy, but since it has repeated itself a lot, we'll discuss it. This is the law of time period. This says that the square of time period is directly proportional to cube of semi-major axis. Directly proportional to cube of semi-major axis. This is the law of time period. Radius is there. So t square is directly proportional to a cube. So a we take it like the radius, the way we take the radius of circular orbit. Here for the ellipse we are taking it the semi-major axis, not minor, semi-major axis. So t square is directly proportional to a cube. Here no constant as such is there which has a specific unit or dimension. We just put a k. So t square is equal to ka cube. Fine. This will be clarified better with the help of numerical. But before we jump to the numerical, you should write down all these points. Write a separate heading, Kepler's laws of planetary motion. 3 laws are there. Sometimes in your 3 markers, you just have to state the Kepler's laws also. Write it down. I'll discuss it. class, answer. It says that time period of planet X around sun is 100 years. Fine. Calculate semi-major axis, weather radii, and you have to calculate basically when it says no semi-major axis. Means calculate radii of the planet. Now see, you know one thing, that time period of Earth, you know, and radius of Earth, you know. So you can write no TE square is equal to K RE square. That is the time period of revolution of Earth around its own axis. What is it? One rotations revolutions time period. It's 1 year. This is 1 year. Radius of Earth, which is one astronomical unit, or you can write, this is not radius of Earth. This is actually, this will be confusing. This is not radius of Earth. This is the radius of the orbit of Earth. If sun is here, Earth is here. This separation we are considering, not the radius of Earth. That is one astronomical unit. The separation between sun and Earth. This is one astronomical unit. 1.09 into 10 to the power 11 meters. So this Tx square will also be equal to Ka cube. Now time period for this X planet is given as 100 years. And this A is missing. So we know we can take the ratio of both the quantities. See, if you take the ratio of both the quantities, you will get Te square by Tx square is equal to K R cube by Ka cube. K will be cancelled. Now put in the values. Earth time period is 1 year. This is 100 years. Years, unit will be cancelled. Same units are there, so we need not change. 100 square. R cube 1.09 into 10 to the power 11 whole cube. From here, you have to find out A cube. Let me know what is your answer coming. This is how you have to solve. And that completes with gravitation also. I'll start with solid straight up. First, write it down. And let me know what's your answer coming. Yes, class. Now the next unit is properties of bulk matter. So in this unit, you have two lessons. One is your mechanical properties of solids, and second lesson is your mechanical properties of fluids, right? So both the lessons we'll be discussing. Yes, so we'll start with solids first. Solids is a very easy lesson. The concepts are also easy. The formula part is also easy. You just have formula based questions. Young's modulus is a topic that we'll be covering in solids, which is very important, that I'll tell you when we discuss that. But before that, see, some of the concepts you should be aware of before. All right, class. Yes. So in mechanical properties of solids, that is your chapter 9, and next fluids is your chapter. Fluids is a very lengthy lesson. Fluids is a very lengthy lesson. It will take a lot of time. Anyways, let's start with this mechanical properties of solids. So when we start with mechanical properties of solids, some terms are there which you should be aware of before we start. So those are the basic terms. You have questions from these terms. It's just that before we start, we should have the knowledge of these basic terms first. But before we go through it, see an example. Suppose I have a steel wire. All right. This is a steel wire and I have taken its specific length. Let's say I have taken this length as 10 meters. Suppose I have taken this length as 10 meters. The steel wire, its length is 10 meters. So what is 10 meters? 10 meters is its original length. This is the actual length of this wire, is its original. Now what am I doing? One end is fixed to the wall, that you can see also I've marked. This other end which is free, I'm inserting a mass. I'm inserting a mass. This end which is free here, to this free end, I am inserting a mass. Fine. Now what will happen as per your knowledge also? What do you think? If a rod is there, a wire is there, steel wire is there, and you are having a mass fix, won't it pull it? The molecules which were present closer. Now the molecules will move away. Molecules which were put closer because of the force that is acting, they'll be moving away. So what will be the case? Look, this separation. See, now what is happening? This mass is present because as soon as I have connected this mass, I am seeing the length is increasing because the wire is expanding. The molecules are moving away and the wire is expanding. So its original length was this at this point. Now what is its length? Its length is at this point. Do you see this extra change in the length? This is some extra length which is produced, which is delta L. This is the change in the length which is produced, delta L. Original length, it was 10 meters. This was the original length. But now the total length, suppose let's say the length which it has increased, this is 5 meters. Now the total length which we are yes. So see, this extra increment in the length, suppose this is 5 meters. So total length now it will be 15 meters. This total length, this will be 15 meters. So initially it was 10 meters original, the actual length of wire. It has increased to 5 meters because of this mass. And the total length has become 15 meters. Now what am I doing? Why is this happening? Reason is that F is equal to mg. This is acting downwards and is pulling it. Gravitational pull force is pulling it. Now suppose I have removed it. Suppose I have removed this. What am I noticing is, when I'm removing this, I'm noticing this. It is becoming back to 10 meters exactly as soon as I'm removing this. So there are certain materials which have the tendency to gain their original shape. This force which acted in the body and produced a deformation. Deformation means there can be increment in the length. There can be change in volume, decrease in length, increase in length, change in volume, increase in volume, decrease in volume, any change in shape. All right, anything can be there. So this is known as this type of force. These types of forces, these are known as the deforming forces. These type of forces are known as deforming forces. So this was a deforming force here. How do we know that this was a deforming force? Because a deformity was produced. The length, which was originally 10 meters, now it has increased up to 15 meters. So this deforming force was there. But if I am removing this deforming force, the wire which was expanding, now this is back to the original small size, original size. So is it valid? Is this property which is occurring valid for every object? No. This property is known as elastic property. This property which I am discussing, this property is called as elastic property. And this tendency, elastic property, you can say, or you can even use the term elasticity. You can use the term elasticity, elastic property or elasticity. So those bodies which have the tendency to regain their original shape when these deforming forces are removed, those bodies are called as elastic body. These bodies are called elastic bodies. It could have happened that the exact formation wasn't achieved. There are certain bodies. Two types of bodies are there in elasticity which we study. One is the perfectly elastic body. Perfectly elastic bodies have the tendency to regain the exact shape. Like originally, if it was 10 meters, after deforming force is produced, is removed, it will become back exactly to 10 meters. This type of body is called as perfectly elastic body. On the other hand, you have perfectly inelastic body. Perfectly inelastic body. Now, suppose it could have happened that when I have removed the deforming force over here is what? Deforming force is basically mg. Because of the weight of the block is pulling it downwards. That's why there is a deformation produced. Suppose this deforming force I have removed, and what am I noticing is that the length is 14 meters, or this is still 15 meters. Nothing has changed. It has removed it has remained in its position as it is. It hasn't achieved the previous new value. It has achieved the new value. It hasn't achieved its original value. So such type of bodies, we call them as the plastic body. Means they do not have the tendency to regain their original shape back. Either they'll gain another shape or they won't. Like I'll give you an example. You have rubber, you stretch rubber, deformation is produced, your hands which are pulling the rubber band, these are the external forces, and these are the deforming forces, because rubber has the tendency to expand. Rubber is an elastic body, rubber has elasticity in it, so it will expand, and as soon as you remove it, removal of deforming force, rubber will again shorten whatever its original length was. But you take, that is why we call rubber as perfectly elastic body. On the other hand, you take clay, you deform clay, make it into a shape. Suppose you have made it into a shape. Now remove your force. with the help of your force, you have again deformed it. So again, your hands are producing the deforming forces. Now leave it as it is. Will the clay return back to its original position? No, clay will be acquiring its new position. So we say clay is a plastic body. All right, let's see the definitions also. Yes, elastic property means the tendency of a solid to regain its shape and size after removal of a deforming force is called elastic property. So deforming force which produces change in configuration, the force which is producing the deformity. Configuration can be anything. It can be length, the change in configuration, this can be length. This can be a change in shape. This can be change in volume. All right. Elasticity is the property of a body by virtue of which it tends to regain its original shape and size when deforming force is removed. Tends to regain its original shape and size when deforming force is removed. Perfectly elastic body says a body which regains its exact original shape and size immediately after removal of deforming force. Like you have example quartz, you have example phosphor, bronze, everything is written on this. Then perfectly inelastic body, a body which does not have tendency at all to regain its original shape and size on removal of even the slightest deforming force you are removing, no changes are occurring in the body. So best example, wet clay and paraffin wax. Write down these definitions. Any doubts you have, let me know. I'll repeat the part. These parts are very important and very basics for your lesson. If you'll not understand these, you'll not be able to understand further. And some of these definitions are asked. Write it down. See now the types of solid deformations which are produced. If the force is producing one type of solid deformation that exists is the change in the length. Change in the length. So if you increase the force, length increases. This force is called as tension. If you decrease the force, if you're applying the force in the downwards direction, opposite direction, which is decreasing its length, we call this type of deformity as compression. The force that acts is called compression. Secondly, second type of deformation that is produced is the change in the volume. Change in the volume. Suppose this is a sphere and I am exerting forces on this. I am exerting forces on it. So it will compress it. A change in volume will be there. Let's assume the original volume was V. Now after compression, its volume will change. So this is the second type of deformation which can be produced. Last type of deformation is the change in shape. Suppose I have applied a force over this original one is the yellow one, or sorry, white one. Suppose you take a very thick book. If you take a very thick book and on its topmost surface, you apply a force. So what happens? The base of the book remains as it is, but where you have applied the force, it displaces forward. So this shift is changing its shape. Earlier, this was looking from the transverse view, it was looking like a rectangle, right? But when you have applied the force, it looks like a rhombus. Suppose this force is being applied, this theta is the angle that is produced. So change in shape can also be produced. You have not those heavy textbook reference books for your class 11. If you apply a force on its topmost surface, it will slide with the base kept as it is. Write down the types of solid deformations. Yes, class. Now talking about stress. So stress is basically what? Suppose the same rod I'm talking about. The same rod which I was referring to is this. Now its cross-sectional area. It must be having its cross-sectional area. Let's say its cross-sectional area. This part. This is A. Force must be acting on it. So stress is basically the in just 1 meter square. In 1 meter square, suppose I just take 1 meter square area. So whatever is the amount of force acting in just this 1 meter square area, that is called as stress. So stress is basically deforming force per unit area. You can write it as F by A. So SI unit will be Newton from force by meter square. The scalar quantity, and for dimension analysis, mLt to the power minus 2 is for force divided by L square for area. So one LL will be cancelled. This will be M. L to the power minus 1, T to the power minus 2. So stress is what? Force acting per unit area. It's very much similar to power. This is very much similar to pressure. You can write the SI unit as pascals also. PA, SI unit. All right, write it down. The stress portion. This is the introduction. Now see, since you do not have a single type of deformity, so every deforming force will not produce only one type of deformity. You have studied 3 types of deformities. So depending upon the type of deforming force, you have different types of deformities, different types of stress as well. So types of stresses we'll see later. First, write it down, this part. And okay, you have your class also with me, no? Those who will write it till here, you can leave. Then take a break of 5 minutes, because then you will have to join it for the next class. And all of you should join Khadija, Khudaija, Leena, Mariam, Nuha for the thermal unit class. Join the class. You have 10 minutes break. Note it down till here. Then you can leave one by one.